In the last video, I defined for you the concept of a Bayes-Nash equilibrium, which is very similar to a Nash equilibrium, except we're taking into account that players don't know everything and they know different things. And so the idea of optimality is that players do the best they can given what they know. So let's apply this idea of a Bayes-Nash equilibrium to a simple model of a Cournot duopoly with incomplete information. So as usual, you've got two firms. Demand is given by P equals 10 minus total quantity, so Q1 minus Q2. So this is just like before. The difference here is going to be that the marginal costs are different for the two firms. So the marginal cost for firm 1 is 0. The marginal cost for firm 2 is either 0 or 4, each with probability a half. So the game is very similar to what we've seen before, except that now player 2 has either a high marginal cost or a low marginal cost. If the marginal cost is 0, we'll say that this is the low type of firm 2 in terms of its cost, which we'll represent by L. And if the marginal cost is 4, we'll call this the high type. Again, this is in terms of the cost, and we'll represent it by an H. Firm 2 knows what its cost is. Firm 1 doesn't. Firm 1 only knows that the marginal cost of firm 2 is either 0 or 4, each occurring with probability half. So what's the strategy for firm 2? Firm 2 has to pick a quantity as a function of its type. Given that firm 2 picks a quantity as a function of its type, its strategy consists of a quantity for each type. So the quantity that you pick when your type is the low type, and a quantity that you pick when your type is the high type. And for firm 1, there's only one thing that firm 1 needs to do. It just needs to pick a quantity because there's only one type of firm 1. The approach we're going to take here is to write down the best response of firm 2 when it's of low type, write down the best response of firm 2 when it's of a high type, and then write down the best response of firm 1 given actions that it would expect player 2 to take when it's a low type and when it's a high type. And then we'll set up a system of equations based on those to solve for the equilibrium. So given some quantity Q1 that firm 2 expects firm 1 to produce, what is the optimal action for a low type of firm 2? Well, the optimal action would solve the following maximization problem. Pick the quantity Q2 that maximizes 10 minus Q1 minus Q2 times Q2. Remember, there's 0 marginal cost, so there isn't any cost, so your profit is just your revenue. So the first order condition is 10 minus Q1 minus 2Q2 equals 0, which means that Q2 has to be 10 minus Q1 divided by 2. So the best response of firm 2 when it is of type L to Q1 chosen by firm 1 is 5 minus Q1 over 2. We could do the same thing and ask what the optimal action for firm 2 is when it's of type H. It solves the maximization problem where it chooses Q2 to maximize 10 minus Q1 minus Q2, which is the price, times the quantity Q2. However, it has a marginal cost of 4, so it pays 4 minus Q2 to produce Q2. So the first order condition is 10 minus Q1 minus 2Q2 minus 4 equals 0, which implies that, so 10 minus 4 is 6, 6 minus Q1 divided by 2 is what Q2 should be. So the best response of firm 2 when it is of type H to Q1 is 3 minus Q1 over 2. So now we have a best response for firm 2 whether it's a type L or type H. So let's turn to then firm 1. So given a quantity Q2L that firm 2 would produce when it's of a low type and Q2H that would produce when it's of a high type, what is the optimal action for firm 1? That has to maximize its expected profit. What is the expected profit? Given this strategy that firm 2 would follow, so given that firm 2 would produce Q2L when it's of low type and Q2H when it's of high type, if firm 1 were to produce Q1, what is the expected profit of firm 1? Well, when firm 2 is of a low type, the profit is 10 minus Q1 minus Q2L times Q1. When firm 2 is of a high type, the profit is 10 minus Q1 minus Q2H times Q1. Each of these occurs with probability 1/2. So the expected profit is this. So the optimal action for firm 1 solves the following maximization problem. Pick Q1 to maximize the expected profit. Simplifying this expression a little bit, we can write it as pick Q1 to maximize 10 minus Q1 minus Q2L plus Q2H over 2 times Q1. So again, we can write down the first order condition, 10 minus Q2L plus Q2H over 2 minus 2Q1 equals 0, which means that Q1 ought to be 10 minus Q2L plus Q2H divided by 2, the whole thing divided by 2. Therefore, the best response of firm 1 to the strategy Q2L, Q2H is 5 minus Q2L plus Q2H over 4. One thing I want to point out here is that this is as if player 1 is best responding to the average quantity that firm 2 would be producing. This is driven by the fact that inverse demand is linear. Now, we've got all these best responses, so we can set up a system of 3 equations with 3 unknowns. So in equilibrium, we have the following. Q2L has to be a best response of the low type of firm 2 to Q1. So it has to be equal to 5 minus Q1 over 2. Q2H has to be a best response of the high type of firm 2 to Q1. So it has to be 3 minus Q1 over 2. And finally, Q1 has to be a best response for firm 1 to the strategy Q2L, Q2H. So it has to be equal to 5 minus Q2L plus Q2H over 4. Let's call these equations 1, 2, and 3. So we've got 3 equations and 3 unknowns. Now all we have to do to find the Bayes-Nash equilibrium is to solve this system of equations for Q1, Q2L, and Q2H. Let's plug 1 and 2 into 3 so we can isolate Q1. So Q1 is 20 minus 5 plus Q1 over 2 minus 3 plus Q1 over 2 divided by 4, which means that 4Q1 equals 12 plus Q1, which in turn means that 3Q1 equals 12. Therefore, Q1 has to equal 4. Now we can plug this back into 1 and 2 respectively to find Q2L and Q2H. Q2L is 5 minus 4 over 2, so Q2L equals 3. And Q2H is 3 minus 4 over 2, so Q2H is 1. So the Bayes-Nash equilibrium of this game is Q1 equals 4, and Q2L, Q2H equals 3, 1. So that's how you solve for the Bayes-Nash equilibrium of this asymmetric information or incomplete information Cournot game.